Good morning. This is the second lecture of the fourth module. And let's recap what we did yesterday. We started looking at several devices through which we do thermodynamic processes. And those devices were selected because that's what we have in real life. That if we need to make a machine, we would make combinations of those and put it together. So theory tells us that there are a lot of things possible. In practice, there are some things possible, and on that also, there are certain restrictions in their use. So we will continue with that, and then we will look at how we can use all of that knowledge of what is possible, what is theoretically possible, but what is practically realizable. And then we'll look at how we can, what the closest one can come to creating a Carnot cycle. After that, we would have also gained experience in saying that if these are the devices on which I want to make a solution or a problem is given, what is the way in which we go about solving it? And so the first part of it is what we have now done. Tomorrow I'll take up examples where we'll start actually putting some numbers and see a variety of problems over there. So this is what we have been looking at: realization of thermodynamic processes. What are the types of devices that we have? These are theoretically possible, and practically, from the world of engineering, there are limitations. And what we have done is, even with those limitations, we have seen what are the implications of those limitations on the thermodynamic performance of these devices. So yesterday, we looked at these devices, positive displacement devices. In particular, something that keeps coming up, and we'll look at it again, is the cylinder piston arrangement, closed system in which working substance does various things. Then we looked at the idea of what is the heat exchanger, and we learned that a major assumption we make in heat exchangers is that heat transfer processes, when they are flowing through a tube, the fluid, they are assumed to be constant pressure processes. So that is possible. Then we looked at compressors, where we take an ideal gas and increase its pressure relatively in large amounts, and fans and blowers, where the pressure rise is relatively small and flow rates are high. And both these, we said, are work input devices, and in the ideal case we said that this would be at best isentropic. And we also saw that the way we get these machines, we do not add heat into these devices. In reality, if it is running above a temperature, there will be a little bit of heat loss from the surface to the ambient air. Then we looked at pumps. We said these are devices that take a liquid and pump it to a higher pressure on a continuous basis. So here is also work input is there, and we said that the ideal case was isentropic, like the compressors, fans and blowers, and what would be the real case where this entropy increases. And we looked at the last machine yesterday was the turbine, and we looked at gas turbine, we looked at steam turbine, hydro turbines, and we said these are work producing devices, and the most efficient way that we can get them, thermodynamics tells us that there should be an isentropic process in these turbines. And we said that if these were real machines where there is some irreversibility in the flow, then operating between the same pressures, what does the process look like? So these were the things we looked at. So today now we will look at another list of things. We will continue some of this I had put up yesterday. We'll now look at a nozzle, then we look at a diffuser, then expansion valve, or something in which throttling takes place, a pipe, tube or a duct flow, just a plain flow. Then we look at mixing of the same substance, not mixtures of two different substances. Then we will look at separation, particularly in a wet region. And finally, we'll look at unsteady processes like filling or evacuation and emptying of a tank or a reservoir. So let's start with the nozzle. So this is a device which accelerates a fluid. In the process, the pressure drops. And a typical sketch of this would look like this, in which the working substance enters here and exits over there. And we make this as a system, saying that the system boundary is everything that is inside this nozzle. And to that we apply various laws. So once we made the system boundary, we see that there is something moving in here, something moving out. So our first step in the analysis is to decide whether it is what is the system boundary. We did that. Whether it's an open system or a closed system. This is an open system. And then we say, well, now I have to apply equations which are the control volume equations. We have one inflow and there one outflow. And that tells us that this is state 1, we call this state 2, that m dot 1 is equal to m dot 2, and then we say, well, what does the energy equation tell us? It tells us that in this case, we make the important assumptions there, that first, it's a relatively small device, and we try to insulate it if possible. So this is adiabatic. There is no heat transfer during this process. Then we also say that there is no work transfer happening across this, so there is no work. And so there are the things that happen, but the size of this is relatively small, so that means that we can safely assume that delta change in potential energy is 0. And the very first assumption, like we did yesterday in all the analysis, steady state. That means nothing changes with time. So we said delta PE is 0. But because this is a device that accelerates a fluid, there is no way we can assume that kinetic energy changes are small. So in this case, what is clear is that V2, the velocity, is greater than the inlet velocity, which is V1. If one of these values is given, say V1 is given, then we don't need to make this assumption. But the important thing then becomes that if we solve the energy equation and simplify it, then we get H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. This is what we get. If V1 is given and the conditions states 1 and state 2 are known, then H1 and H2 are known, we can calculate V2. So that's the analysis of a nozzle. And this doesn't matter whether it is an ideal gas or a vapor, the processes are the same, and we have to show it on a TS diagram. If we are looking at something which is in the wet state like that, then a nozzle ideally would be without any irreversibilities. So this would be S equal to constant or an isentropic process inside this. So if the initial state is there, we can say that ideal case it comes down to this pressure. So this was P1, this is P2, and this is what the nozzle would do. A real nozzle, this is the isentropic part, a real nozzle would have irreversibilities and it would come to this point. We could have put a nozzle there also and accelerated the fluid there. Or if you are far away from this dome in the ideal gas region, say somewhere here, then also it is the same thing. This is 1, this is 2, and the gas is accelerated. If there are irreversibilities, the gas will then reach this point. This dome will not appear, but this is the process. So the process actually looks the same as that of a turbine, but the difference is that in the case of a turbine, there is work output. In this case, W dot CV, the work output or input in this is 0. And the drop in enthalpy goes to increase the velocity at the outlet. So such devices are used in turbines, compressors, and many other applications where you want to accelerate the fluid and get some benefit out of that. So that's a nozzle. And the opposite of the nozzle is what is called a diffuser. So here we look at what is a diffuser now. So this is a thing which decelerates a fluid. That means in the direction of flow, the velocity goes down and pressure goes up. So what's happening here is that we have a flow coming in, and then there is the area opening up and the flow goes out over there. So we say that the diffusing part is the one where the area is large. So we say this is our diffuser, the control volume. So this is the system boundary, you can say. And there is one inflow taking place here. So this is state 1, inflow into the system, outflow is there, state 2. So with that, we put this thing together and say that first, this is an open system. So we have to apply the control volume approach, and we use the flow equations that we have developed. This is 1, this is 2, entry and exit. Again, like the nozzle, here also we assume something. First, steady state. The second assumption is that there is no heat transfer, so this is adiabatic. Q dot Cv equal to 0. There is no work. W dot Cv equal to 0. And changes in potential energy, these are very small, they are. But because the primary job is to decelerate a fluid, it means that velocity changes are substantial. That is the main purpose of this device. So kinetic energy change being 0 is not an assumption for the diffuser. So there is one inflow, one outflow, and the energy equation becomes exactly the same what was there earlier for the nozzle. This is V2 square by 2. And so in the direction of flow, the enthalpy will change and you have decrease in the velocity. So if you plot it on a TS diagram, if it is an ideal gas, there will be a state there. It is ideal case if we assume this is that S is constant, isentropic. So it starts from here and it will go, say, there. State 1, state 2. If it is a real case, then this is the isobar. This is the isobar here. Entropy has to increase, so this will go over there. And you can check from the TS diagram that what it means is that this, it has been taken to the same pressure, but now the temperature has gone up. So this was 2 isentropic, this is the 2 real case. The process looks very similar to that of a compressor, but the difference is that here work transfer is 0. The only change that the enthalpy difference does is because of the velocity change. That's the difference. And if you were near the dome, the same thing would happen, that if your initial state is over there, then we would like to bring it up there and increase the pressure. So that's what diffusers do. And you use diffusers in places where you have very high velocity, which you want to reduce. And one of the places where such a device is used is the exhaust of a turbine, where as the gas goes through and expands, its velocity also increases, but we cannot increase the area so much that the velocity can be kept low. So what happens is the exit velocities are high, and then we do not, if we want the kinetic energy to be recovered for some purpose, we can then put a diffuser there, recover some of that energy, and then throw the gases out. You will also see this in rockets, where at the bottom you will see a device looking like this, where you got high velocity fluid coming in, low velocity fluid goes out. In the process, the pressure increases, and this is what generates the thrust on rockets. So this is a very important part in the design of propulsion systems. The way we achieve nozzles and diffusers, although I have drawn it here as a pipe, in turbo machines, we achieve this as making a passage between 2 consecutive blades. So if you look at 2 blades and we draw the shape there like this, so this is say 1 blade, and this is the second blade. Then the purpose of this is that as the gas or the steam flows through this, we take this as a system here, and what I've drawn is a blade of this cross section which is normal to the plane of the paper, and there are many such things on a shaft. So they make a circular thing which looks like a turbo machine rotor or a nozzle. But the thing is that when this enters here, it sees this much area. Normal to the paper, the height is the same. So this is the inlet plane. At the outlet, this has decreased. So these two things together produce a flow passage where the area decreases. And this would mean that this would act like a nozzle that will accelerate the fluid. So between this inlet state 1 and the exit state 2, H2 will be less than H1, and the velocity at 2 will be greater than velocity at 1. So that's what one does in turbines, where we have high pressures, say steam or gas, we accelerate it, and then we pass it over a rotating set of blades, which imparts momentum to it, and that's what causes the power output from a turbine. The opposite is done when we look at compressors. So you have the same shape, but now you are putting in from this side and you decelerate the fluid. So this is a realization on turbo machines. The idea is that we create passages. It does not necessarily have to be concentric, it doesn't have to be straight. It could be of any shape, and we can get this type of performance from the device. The next thing we are going to look at is a device which we call something we will call a throttling valve, but some places also known as an expansion valve, and popularly we also see these as pressure regulators. So all of them in construction would be slightly different, but in all these cases what we have done is that we just have a small constriction in the flow, and this flow could be passage through a valve, which means that there is a body into which it enters from one side, and we have a small constriction there. As the fluid goes through this, there is a big pressure drop, and that's all happens over at the outlet. This is a small device, so what one does is that we assume that this is a steady state system. The control volume would be like this, or in this case it could be like that, and here we have something coming in, going out. This is state 1, this is state 2. So this is an open system, and we have to apply the control volume approach. We assume that it is steady state, there is no heat transfer, adiabatic, there is no work transfer, it is just a simple stationary device, nothing moving. Then we also say that here velocity at the inlet and outlet are comparable. They are not very drastically different, so it's not like a nozzle in any sense. And of course it's a very small device in most cases, and we can say that changes in potential energy are zero. So the conservation of mass equation tells us that m dot 1 is equal to m dot 2, and the conservation of energy tells us that H1 is equal to H2. And so this type of a process is isenthalpic. Inlet outlet enthalpies are the same, but what we have done is we had a higher pressure, high temperature here, we got a much lower pressure on the outside. We would know from the second law analysis that S2 is greater than S1. Throttling is a hugely irreversible process. Which would also mean that you would like to avoid it as much as possible, but then there are certain practical aspects of the throttling process which are very, very nice. And where do we see throttling taking place? Firstly, we can see that in all your refrigeration cycles, where what we have done is that is the pH diagram, and on this we can plot the dome. And after subcooling the liquid from the condenser, we have to bring it down to this pressure. One option is that, okay, let's put a small turbine, generate some work, and come to this state. Entirely possible. Thermodynamically, it is nothing can be, it's entirely feasible. Practically, for the size of the machines that we have, refrigerators and air conditioners and even large devices like central air conditioning plants, the work output of this will be so small, the machine is complicated, and second, somewhere it is handling a liquid, somewhere it's handling liquid plus vapor. That makes the machine very practically impossible to make in the engineering world. So we do not have work transfers taking place like this. And as we saw with turbines, in general and pumps, we do not want any work producing device that operates like this or operates like this or there or there. We want work producing devices to either handle only a vapor or a gas or only handle a liquid, not mixtures of these two. Such machines cannot be made. Okay, so in the refrigerator, we cannot put a turbine. The second option we just learned, why not put a nozzle? We can accelerate it, it's an isentropic process, but the trouble is that by the time you drop the pressure, the velocities are so high, it becomes difficult to manage the machine. So the next easiest thing one does is to just throttle it. And throttling is an irreversible process. We don't know exactly what happens in the intermediate states, but it brings us from there to there. And that can be done either through a valve, or we put the refrigerant suddenly through a very narrow tube where there's a very large pressure drop. That's all it does. In the process, a subcooled liquid becomes a saturated state and the wet mixture that you get here. So that's what we use throttling for in all refrigeration systems. The second application that you would all have actually seen is your LPG stove. So on the top of the cylinder, you have a small device, something looks like this, and this is sitting attached to the top of the cylinder, and from one side of this, there's a tube going out. That is the pressure regulator. Without that, we cannot use the LPG regulator. What it does is that there's a very small opening over here, which is controlled by an automatic spring device, which senses the pressure over here, it senses the pressure over here, and depending on the difference of the pressures, it adjusts the position of this, so that inside here, which is saturated vapor at the 3 bar, 4 bar, something like that, that is reduced and brought down to a pressure of 600 millimeters of water column. That is a throttling process. So we have just throttled it from say 3 bar or 4 bar, somewhere in there, to 600 millimeters of water column. That's a much lower pressure. So this is a very small opening, like a millimeter in diameter or so, through which this vapor passes. There's a lot of friction that it goes, and its pressure drops, but enthalpy remains the same. There is not much change in velocity. Potential energy changes are very small, and you get constant pressure over here. So that's the device of this, and that's why it is called a regulator. That no matter how much gas you are using, whether you have gas on low flame or on high flame, this will always put out, by adjusting itself, 600 millimeters of water column pressure here. Where it begins to have a problem is that when the cylinder is getting empty and the liquid is all gone, then 3 bar pressure, as you keep drawing the gas, will start decreasing. In which case, after some time, this regulator cannot do its job. This pressure begins to fluctuate, and you see that the stove is now giving an unstable flame, and that's a good indication that the cylinder is about to go empty. So pressure regulators is another very important device, not just here in LPG, but you can see any machine which operates on CNG, as CNG operated bus or auto rickshaw or taxi, the cylinder pressure is 200 bar. You cannot put that into the engine. So there's a pressure regulator, maybe 1 or 2 stage pressure regulators that bring it down. From here, pressures could be as high as 200 bar and brings it down to again something like this pressure, few 100 millimeters of water column. So these are also used in industry, where you say that I need to have say steam coming into a device at 10 bar, but your supply comes anywhere between say 11 and 13 bar. You always give some margin there, and so you do a small amount of throttling so that outlet pressure is always 10 bar to the device that you want. So these are very commonly used. Because of this very precision movement inside this, these are very sophisticated devices, and the engineering of this is quite a challenge. But the fact is that these are commercially available. A lot of these are available for many different applications, and they are used very frequently in process industry. Okay, so this is the idea of a throttling valve or a pressure regulator or an expansion valve. It need not even be a valve, as I mentioned. In refrigerator, it could just be a long, very thin tube through which, as the refrigerant goes, because of the frictional pressure drop, it achieves the purpose of throttling. Okay, so that was what happens in a pressure regulator or an expansion valve. And it's a hugely irreversible process. So if I have to show this on a TS diagram, and the saturation dome is say somewhere there, the constant enthalpy lines, they run like this. These are constant enthalpy lines. So the throttling process on the pH diagram, which look like a straight line, say between this pressure and this pressure, it will actually follow a path and come finally to this state. So this would be the throttling on the TS diagram in the case of the refrigerator. But if you are throttling superheated steam, then it could come from there to there, or maybe there to there. So in every case, it goes only in one direction. It's an irreversible process, so the opposite process is not possible. Unlike say, nozzles, unlike diffusers, turbines, pumps, all of those ideally we are shown to be isentropic process, which means that you could exactly do everything in the opposite side and run it in the other mode. Here it is not possible. This is hugely irreversible. And the only other thing that comes out to be interesting is that the constant enthalpy lines further away become constant. And so this region, which is the ideal gas behavior, these lines are constant, which tells you that if you throttle an ideal gas from there to there, this should be a dotted line, it's an irreversible process. Throttling is a constant temperature process, isothermal. And that means that that's only when the velocity changes are very small. Other examples of throttling is like you suddenly let out steam from a pressure cooker, or there's a puncture in a tire. So what you have there is say a vessel or a device which has a very small opening, and through which the fluid is leaking out in this case. We all know from experience that if air leaks out and comes out here at high velocity, it also feels cold. That means compared to this, the temperature has increased. So this is opposite to what we have just seen over here. And the reason why that happens is that here velocity has increased quite a lot. So there is part of it, some of it is like a throttling process, some of it is like a nozzle. In a nozzle, if you increase the velocity of a gas, which would happen here to there, you could see a drop in temperature, and that's what we see happening over here. So this idea is exploited in gas-based air conditioning systems, where you expand the gas and you produce cooling. And an example where that type of a cooling is used is all aeroplanes. So inside the plane, the air is either heated or cooled. If it is hot outside, on the ground, it is to be cooled. So that's what is done. And when you are up flying at 10,000 meters, the air temperature outside is minus 40 degrees Celsius, in which case the compressed air, which is at a higher temperature, is slightly throttled and put inside the passenger cabin to make it nice and cozy. But those are not entirely throttling process. You are partly using the effect of a nozzle also. Okay, so that was throttling. Now we come to something which is somewhat trivial. You wouldn't really find that being discussed in many books, but this is essential to completing a flow cycle. And what it is is flow through a pipe or flow through like water flowing in a pipe or steam flowing in a pipe or oil flowing in a pipe or through a tube. Tube means basically inside diameter is relatively small. Pipes inside diameters could be very large, all the way down up to meter, 1.5 meters, 2 meters. Tubes are small in diameter, few millimeters, 5 millimeter to 8 millimeters types, and ducts. So duct is the term used into which we have a gas or an air flow. So if you have seen air conditioning buildings and you have big square or round things moving around through which air is going, those are ducts. Now, why do we need these? So yesterday when I started off, I made a picture of a refrigeration system and I said that there are 4 items there. There is an evaporator, there is a condenser which gets compressed gas from there, and evaporator, expansion valve, this could also be a symbol for it. And the thing is, these devices we have just seen now, what is the thermodynamics of that? To make a system practically, we have to connect them in the right sequence. And this is essential to all flow systems and flow cycles. So what we are showing here to here is a pipe. Here to here there is another pipe. Here to here this is another pipe. Here to here is another pipe. And how do we treat these in the thermodynamic analysis? That is what we are going to be looking at now. So ideally what we have is we can make a pipe and we say that, well, if it perfectly, first, what is the system boundary? And the system boundary we say is just this one. All the fluid inside the pipe over a certain length. And it tells us that there is inflow happening here, this is state 1. Outflow happening here, this is state 2. And this immediately tells us that first and foremost this is an open system, which means that we have to apply the control volume approach for analyzing this, which tells us that one in assume, first we assume steady state, and then we can say that changes in kinetic energy are pretty much zero. The pipe is neither accelerating nor decelerating the fluid, ideally speaking. And in 2 cases, ideal case, we can say this is isentropic. In the real case, when it is irreversible, it is because of friction in the fluid and between the fluid and the walls of the pipe, because of which there is a pressure drop, because of which there is a enthalpy drop. So that's what real pipes do, and we know that there is a pressure drop in that. The theory of this you learned in a course in fluid mechanics. But thermodynamics tells us that under these assumptions, this is what will happen in a pipe, and if we either assume that this is isentropic, there is no work transfer in this, so W dot CV equal to 0. In the ideal case, Q dot CV is also 0, but even if this is 0, internal irreversibility if are there, this could cause a drop in pressure. So what we do in treating pipes in a thermodynamic system is that if that's the thing and we are looking at a TS diagram, what we are saying is that if a flow is taking place, then the state will remain the same. But if it's a real flow, then this was the isobar through which this point was there. There will be a pressure drop, it will come here. Pressure drop being an irreversible process, and since there is no heat input output, enthalpy is remaining the same, there's sort of a throttling type of a thing happening here. The state here will come down. That's what would happen in a real pipe. On the PS diagram, when we have the dome there, we say that okay, we are pumping it from through the evaporator from here to there. Ideally, we assume it to be a constant pressure process. Practically, the pressure will be slightly less, and so the process will actually be something over there. So practical design of these type of systems, we will take care of pressure drop in every one of these pipes. Most of them are insulated, so we say, well, insulation is there, and we can, as a first approximation, we can say that adiabatic Q dot CV is 0. And then the diagram which looked very simple will actually start looking a little more complicated. I'll just make one diagram as an illustration, and this is on the pH diagram. So this is the dome, and the ideal cycle says this is the compressor outlet, this is the compression process, this is inlet, this is outlet, and we assume that the condenser, ideal condenser, would be like this. The real condenser, it will get to a slightly lower pressure than this, and so the process then would have to be shown by this line. Throttling, of course, did reduce the pressure, and this process, though, if you want to come back to this point, we would then have to go through this. This would have been the ideal case, but because the pressure drop takes place, it will come over there. So that's the sort of a changes that happen to the diagram when we do the analysis of real cycles. We will not go into the full details of that part right now here, but the fact is that while we will do analysis of the ideal cycle there, assuming that there is no pressure drop in the pipes, we should know that if I have to treat the pipe, there is a very simple way by which the thermodynamics tells us what we should treat it as, and we can factor that into the cycle analysis. Ducts are nothing but air flowing through them, and the same theory applies to duct flows. Where this is important for pressure drop and all these pressure drops have to be ultimately taken up by the work input device, which in this case is the compressor. If it is a water system, then all the pressure drop in the pipe has to be taken care of by adequate pressure build-up in the pumps. So your pump design, your compressor design, the fan design, they depend on the design of the pipes and also pressure drops which will take place within the cooling coils or some heating coils or some other tubes. So that's where this is important.